Sheffield in the United Kingdom with Steve Reynolds. And prior to that, he studied computer science and physics in Technical University of Madrid. Yeah.
Thanks. Thanks, Bill, for inviting me to come to speak here today. Please feel free to interrupt to ask in the presentation. I'm going to present a class of probabilistic models which are pretty general, latent variable models, and particularly continuous latent variable models, meaning that all variables we are going to deal with are continuous, the ones we are going to care about. And these models can be used for two interesting problems of pattern recognition, which are dimensionality reduction and data reconstruction. So these will be the three main topics of the talk. Now, the models can be applied generally to a number of applications of problems, but I will make a special emphasis in some speech applications. So first, I will give a very brief example of what a latent variable model is able to do. Then I will go through the theory of continuous latent variable models and the types of models that we have here. I will demonstrate how dimensionality reduction can be useful for speech, and in particular, I will use electropalatographic data. And then the last part will be the longer one, reconstruction of sequential data. And in particular, I will talk about the acoustic-to-articulatory mapping problem. So continuous latent variable models do the following. Imagine you observe some phenomenon in nature that you measure in the form of vectors sampled in time, and those vectors are, generally speaking, relatively high dimensional. And you know, however, for knowledge of the domain, that this phenomenon has intrinsically a few degrees of freedom. And just because you're measuring those dimensions doesn't mean that the space is fully populated of those points. Those points are going to be constrained to some low-dimensional representation there. And you want to model that representation. So this is what latent variable models do. Now, to be specific, imagine you have a plane traveling around the Earth. So it can be over the United States, it can cross the Atlantic, go to Asia, and so on. The position of that plane can be represented exactly with the x, y, and z coordinates with respect to the center of the Earth. But we know that the plane cannot fly too high or too low, so it's going to be constrained to actually be around the surface of the Earth, which is a two-dimensional thing. So we could represent the position of the plane more intuitively with respect to an observer in the Earth who lives on the surface of the Earth, and also more parsimoniously just using two variables, the latitude and the longitude, for example, or any other two variables on the surface of the sphere. So that would be the intrinsic manifold that we are after. And dimensionality reduction will be the particular coordinate change from the x, y, and z coordinates to the latitude and longitude. And vice versa will be the mapping that I am representing here from the low-dimensional representation to the high-dimensional one. Now, that would be dimensionality reduction. What reconstruction of missing data means is, imagine that the pilot of the plane transmits the position x, y, z of the plane at any time in the trip to some station, but that due to interference or something, sometimes the x coordinate doesn't make it through, and then you get just the y and z. At the next time, you may get everything. At the next time, you may not get anything. You may get y and z, any combination. So you could represent the data as a matrix where you have your vectors, raw vectors, in time, and components of the vector horizontally, and there are holes there in a relatively, in principle, arbitrary way. There may be now some specific patterns for that. But what you want now is to fill in those holes and to recover the original complete data. That will be the problem of sequential data reconstruction. And we'll show how you can do this with this class of models. Now, this is the schematic representation of latent variable models. You observe the space, the x, y, z coordinates in the example I mentioned. And those points you measure fall in a low-dimensional manifold. Now, of course, there is noise, like the plane can go slightly up and down in the radial direction, but we don't consider that as an intrinsic coordinate. That would be accounted for by noise. So once you are in a point in this manifold, I assume that there is some noise model on top of it that accounts for that. Now, the intrinsic representation in terms of latent variable models would be latitude and longitude in that example. And then you give a value of latitude and longitude that gets mapped to 3 dimensions, and there you add the noise, right? And then what we have is and you have also a prior distribution in the latent space, which tells you how likely it is that that particular plane is at a particular longitude and latitude. That would depend on, for example, what the root of the plane is. So the prior distribution, P of x, in the latent space, the mapping to high dimensional space, and the noise model, P of t given x. So how likely it is that any point in space, any x, y, and z point, could happen given that the latitude and longitude were whatever they are. That's the noise model. So altogether, that gives you a probability distribution jointly on the variables x and t, on the latent and observed variables. And that's that's the most complete representation of this model. With that, we can compute anything we want, like conditional distributions of observed variables given latent ones. This is just the noise model. Or the opposite, which is how likely it is that this particular latent variable value there is given that we are here. Given that we are at x, y, and z, what is the probability distribution on the latitude, longitude, and space? Right. So to be specific, in one of the examples I will mention later, the observed variables will be the position of the articulators in the vocal tract, for example, the position of the tip of the tongue, the dorsum, or the lip, upper lip, and so on, various landmarks in the vocal tract, plus some representation of the acoustics, for example, MFCCs or something. That can be observed in principle. Maybe difficult for the articulators, but they can be observed. And we know that because of the physical constraints of the vocal tract, that's going to have a few degrees of freedom, fewer than what we actually measure. We can measure up to, for example, typically 13 MFCCs and something like 10 to 20 X positions altogether, 10, for example, XY positions for the articulators. That adds up to 40 or 30 or something like that. The speech system should not have that much. At least we can do with much fewer degrees of freedom. That's what we will do later. And the reconstruction problem would be, for example, I know that the acoustics are these. What are the articulators that correspond to those acoustics? That would be the acoustic-to-articulatory mapping problem. And it's known to be a multi-valued problem. You can have different vocal tract shapes that give you the same acoustics. So that will come later. Now, how you operate and estimate with these models? Well, the full representation is P of t, x, which can be put in this form. And then for different functional forms of the prior distribution in latent space, P of x, the mapping F, and the noise model, P of t of x, then you will get a different functional form there. And you want that to be as general as possible. Now, you cannot always integrate those things. Then some models are solvable, and that's the ones that we can deal with and estimate, and others we can just imagine. Estimation of these models is done, as usual, with maximum likelihood. So you have a sample of observed points. The latent points, you never observe them, you invent them. You have a sample of observed points, t. By the way, t in my notation will always be the observed variables. It's never going to be time or anything like that. And then you can estimate, for the particular model, you can estimate the parameters of the model, the parameters of this, and the function f, using an EM algorithm. And once you have your model fixed, the parameters are frozen, and then you play with the variables x and y, x and t, then you can do dimensionality reduction given a point in observed space by looking at the conditional probability of in the latent space given that point, which you compute using Bayes' theorem. And then you derive a dimensionality reduction mapping by picking a point of this distribution that hopefully will be picked in just one point. But that will be something we'll talk about later. Now, some specific latent variable models are obtained by giving functional by choosing functional forms for those things. And there are several that I'm sure here you must have heard of. So the earliest one that appeared at the beginning of the century in psychology and statistics was factor analysis. Here what you say is the prior distribution in latent space is normal 0, 1, standard normal. The mapping is just linear, and the noise model is diagonal normal. And then how does the induced probability distribution of surface space look like? Given that I have said that I have a normal distribution here, that this is linear, and that I have a normal noise model there, how does the P of t look like once I take it out? Well, it is a constraint Gaussian. That means it's going to be Gaussian, but it cannot have any covariance matrix. It's going to be aligned in a specific way. It's going to be using fewer parameters than a full Gaussian. And that's because we are representing them in this low-dimensional space. Principal component analysis can be interpreted in a similar way, as can ICA, independent component analysis, and independent factor analysis, model published a couple of years ago in neurocomputation. The most interesting one here is the generative topographic mapping. And the reason for that is that it is the only one that has a nonlinear mapping here. And we need that nonlinear mapping for most problems. So what this model has is, it has a Gaussian noise model, and it is spherical, the same in all directions, although I have extended it to a diagonal one. And the distribution in latent space is uniform, but we discretize it, just because otherwise we cannot integrate it out. So what we end up having is a grid in latent space with many points there, all of them equally likely. But we are able to integrate that, and by taking a lot of those points, we can approximate very well the density. And then the nonlinear mapping is a radial basis function mapping. Right. So you can just think of it as being a model that is going to fit relatively well the manifold by putting a lot of small round Gaussians on top of it. But the centers of those Gaussians don't move arbitrarily like in a normal Gaussian mixture. They are constrained to lie on that function I am defining here. And when I learn with EM, it is this function I am modifying. And with them, I am carrying away all the Gaussian centers. So that's why it's a constrained Gaussian mixture. Unfortunately, the problem of this model is that it is exponential. The complexity is exponential in the latent dimensionality, which limits it in practice to 2 or 3. I have used 1 to 2 dimensions. Right, so the first application is dimensionality reduction, and let me introduce the problem of electropalatography. Electropalatography is a technique that consists of measuring the contact pattern between the tongue and the hard palate during a continuous utterance. So what it consists of is a plastic palate that the speaker feeds to his mouth, containing a lot of electrodes in a grid like that. And every time that the tongue touches on the palate in the appropriate location, then that electrode switches on and you record the whole thing. And then you get that many times every second. It's normally 200 hertz, the sampling rate. And then what you get is a sequence of things that look like this. Now, in this representation, the lips will be on the top, the velum, the throat will be here, and around we will have the teeth, and this is the palate. So when you say, for example, the letter D, you are putting the tongue against the alveoles, and therefore this part certainly has contact. When you say a velar consonant like K, then you are pressing against the back of the mouth, and you get that particular pattern. What happens with it is that usually you have something like 62 electrodes, therefore a binary 62-dimensional vector at every time, and you sample that many times per second, so it's difficult to analyze the raw data, and you want to reduce it. What phoneticians have done, and people working with EPG for applications like speech therapy and speech learning and so on, is that they have come up with some data reduction methods. They are all linear. What they do is that they compute the weighted sum of a few of these electrodes. For example, if you want to know whether a particular EPG has a lot of contacts around the alveole, you sum, say, all the electrodes in this part. And then this will give you a high value for that one and a 0 value for this one, say. And so on. You can sum different parts to account for asymmetry and things like that. Well, what I did here was to train several Latent-Variable models and reduce dimensionality, and also look at the representation that that gives me. I show first these linear ones. So there are several here, but the one that really matters is factor analysis. What I did was I trained a factor analysis model with 9 factors in this case. And these are the loadings of the appropriate matrix. It means that I multiply that thing times an EPG frame, and I get a reduced representation along that particular factor direction. And what you can see is that they indeed coincide with some of the ad hoc indices I just mentioned that phoneticians use. That one would count, well, it counts everything, but it counts mainly the electrodes that are around the alveoles. That one, the velar ones, and so on. But what the advantage that this has is that they are adaptive, that they are telling you much more than ad hoc indices, because they are extracted from the particular data set I used. And that data set, in this case, was for a particular speaker. So they are telling me, for example, that the speaker uses the tongue in speech relatively symmetrically, right? But I have data from other speakers where there are some cases of asymmetry, for example. But there are speakers that have a tendency to have much larger asymmetry, and you can see that immediately from this representation. So on the one hand, these results confirm that some of the indices used by phoneticians are indeed meaningful as the data set, but on the other hand, they are also suggesting you new ones. And from the point of view of dimensionality reduction and reconstruction, so how well the information is preserved by these methods. Say that you take an EPG, you reduce it to 1, 2, or whatever number of components, and you take it back and see what the error is. That is the square reconstruction error. The log likelihood is the log likelihood of the appropriate model when I trained it. So I'm plotting here a number of models. In the x-axis, for factor analysis and PCA, I have the number of factors I used. That is the number of latent dimensions. So 6 means that I used 6 dimensions, 6 latent variables. For the GTM model, I just use in all the points there only 2 dimensions. And the difference in the points is how flexible the actual nonlinear mapping is, specifically how many radial basis functions I used to implement it. But the dimensionality is still 2. I'm getting just 2 components. And what you can see is that that method beats just about every other method, no matter how many components they are using. And also for reconstruction error. For PCA, which is the optimal linear mapping for dimensionality reduction, you have to go to something like 7 or 8 components to attain the error that GTM is getting. One particular model of GTM just using 9 radial basis functions is getting with 2 dimensions. What this is saying is that this data doesn't have a very high dimensionality. With the 2 dimensions of GTM, you can account pretty well for it, but you need a nonlinearity. If you just use a linear method, you really have to go to many more dimensions, many more degrees of freedom that data has. Now, you can look at the 2-dimensional representation during an utterance, and I show here GTM and factor analysis. So, this corresponds to the fragment cant2 of that utterance there. And you can see that the projection of the appropriate EPGs on this 2-dimensional map follows that path there. Now, it's immediate to see that the velar consonants K, G, and are all mapped up there, while the alveolar ones are in this corner, and so on, some vowels there. So what we are getting here is a map of articulatory categories corresponding to the EPGs. And this can be useful for speech learning and therapy, for example. And that's the representation with factor analysis, using the first and second factors only. You can choose any combination you want for 2 dimensions. I generally observed that the GTM representation was far better than any one you could get with the factors. Another thing that this map shows you is also discontinuities in the data. Most physical variables tend to vary with time in a continuous fashion, and electropalatograms should do the same. There are conditions under that cannot happen, but in principle it should do. And when you see big jumps here between continuous frames, that would be telling you that there is some discontinuity there for some reason. And in this case, it is you can see the corresponding frames there, and you can see that from that one to that one there is a massive variation, even though they are basically consecutive. The reason for this particular one, I think, is just that the sampling rate is too low, and you are just missing intermediate frames. So this would suggest you to use a higher one. However, for most of the utterance, the sampling rate is much better than necessary. So it just happens that the APGs change very fast at some positions, at some particular sounds, but don't change that much in others. Okay, so I finish here with the first part, dimensionality reduction, and I will move to the sequential data reconstruction one. Before getting into the method I have developed for this, I am going to talk for a little bit about the acoustic-to-articulatory mapping problem, which is a particular case, as I said at the beginning, of reconstruction of sequential data. Reconstruction in the sense that along an utterance, along time, we get the acoustic and the articulatory vector, but we don't see the articulatory one. Can we infer it from the acoustics at any time? That's the problem I'm going to approach here. So what happens is that, as I said, given a particular acoustic waveform at time t, there may be, not always, but there may be several configurations of the vocal tract that produce that. And this is what ventriloquists do, for example. They can speak without moving the lips. That means that they are compensating with the rest of the vocal tract. This poses problems because from here to here, the mapping is univalued. You give your vocal tract representation, and that gives you the acoustics, only one, because it is a causal model, a physical model. And then you could learn this mapping from articulator to acoustic representation using a neural network, for example. There would be no problem with that. But to learn the inverse one, you cannot just use a simple mapping approximator, because that's going to give you one value, and it's going to be usually the average of several values, which is going to be in general wrong. So the approaches that have been applied for this include the best one, which actually happens to be a particular case of the method I will present, is using a code book and searching with dynamic programming in a way I will explain later. Then people have applied neural networks that, as I say, don't give a good result, and also assemblies of neural networks that try to learn not the average mapping, but each separate branch of the mapping. You map a neural network to each branch. Other problems to which, well, this also has biological implications about what internal inverse models for speech production and perception are, motor control in general. So this arose a couple of decades ago with the motor theory of speech perception, which has been heavily controversial, that postulated the existence of two things in the brain. One, a motor code, a set of primitive gestures, articulatory gestures that get translated into the acoustics, and then a translation module also in the brain in a neural substrate that accounted for that translation. So from acoustics, from articulatory parameters to acoustics, and vice versa, both mappings. That hasn't been demonstrated so far, but computationally it's very attractive, and there have been many models based on that. And the same can be applied to other types of control, like
Yeah. Is there any reason to believe that this mapping is in fact invertible? I mean, why should it be one-to-one?
No, I am saying that it is not one-to-one.
It is not one-to-one.
It's not one-to-one.
So in what sense are we inverted? How can you invert something that's not one-to-one?
Right. So what happens is that at a given point, you have several possible values that could be mapped there. Which one do you choose? Well, you can choose the one that across time, a long time, the one that gives you the smoothest trajectory, because the physics of the vocal tract have that constraint. You could in principle just choose randomly. Here I select this one, for the next frame I select this other one, but the jumps between them would not be realizable with a physical system, or would be very difficult to realize, and they just don't happen. So by enforcing that, we are able to break that non-uniqueness. Now, a similar inverse problem happens with arm movement, and I will explain that later. And also, this problem is interesting because recently there has been quite a lot of interest in introducing production information in acoustic models to help improve the recognition rate. And a representation in terms just of articulatory parameters is supposed to be more parsimonious, less variable. It would account for co-articulation and a number of other things. And then there have been some approaches to that. One would be to just augment the acoustic vector with the articulatory one if we can get it. And it was shown that using that combined vector actually gets better recognition. And there are also analysis by synthesis models, like the original ones from Raimobakis 10 years ago, and then recent versions of that, like the hidden dynamic models. Now, this problem then is, as I said, a particular case of reconstruction of missing data. And there are others of interest to speech. The speech ones are on the top. Another one that is receiving attention recently is audiovisual mappings. It is also known that, of course, a person can transcribe a message just by listening to the acoustics. But if you have also the visual information of the facial features, that helps a lot, particularly in noisy environments. And deaf people can read lips. So it means that information about transcription is in both sides. Now, if we have both, then of course we should be able to get better recognition. And this again poses the problem of how do I infer the facial features, how the face looks just from the acoustics, like how open the lips should be, for example, and vice versa. I give her this face shape, what is the person saying? And then a third problem is reconstruction of occluded speech. In this case, there is some noise source or something that is interfering with the signal broadly across the whole spectrum. This is the spectrogram. You can see the formats barely there. And now, at each given point in time, some of these features may be completely obscured by the noise, and some of them, because they are loud enough at that particular energy band, can be received without problem. So some are missing and some are present. Can we recover the missing ones, given the present ones, and somehow accounting for the variation in time of that? Like continuity in the case of the articulators, there is some continuity here in terms of the format, but that's a much more elusive kind of continuity because they break often. They are not completely continuous. And there are other problems. An interesting one is the robot arm I mentioned. Here, the position in X and Y, this is a planar robot arm. The position in X and Y coordinates is given by the angles at the joints, θ1 and θ2, and that's a forward mapping, which is univalued. But the inverse mapping, that is, I tell you XY and X2, X1 and X2 are here. What are the joint angles that put the arm there? That's again a multi-valued, in this case, by valued mapping, because you have this position here, elbow down, and you have the elbow up position, and both map in the same place. So when you move around the arm, you want to make sure that you don't change from elbow up to elbow down at some point, because that's not physically possible. So you have to be careful when reconstructing that. Okay, so in the rest of the talk, then I will present the reconstruction method in an abstract way, but some of the notions have already come up, and I hope it will be straightforward. And it's actually quite simple. So this is the definition of the problem. I have my original sequence of data here. Raw vectors are my vectors in, for example, the acoustic vector here and the articulatory vector there. And I get that in time. So I have a d-dimensional problem measured with a sample rate, and I may get altogether n samples. Now, for whatever reason, some of these values get missing where the black things are, and then I don't see the red ones here. I just see those ones there. So at this particular point, this one, and that one are missing. Can I recover those ones from these ones, and also using the rest of the data? That's the problem. And I will assume that there are two kinds of redundancies that help me to break that non-uniqueness problem. One is what I have been saying from the beginning, that there is a low dimensionality of the data. If the data is low dimensional, it means that the d dimensions I observe, I don't need to have all that. I can do with only L if cleverly chosen. And that means that my data, instead of living in a d-dimensional space, they live in a low-dimensional manifold. Like the case of the Earth, I said at the beginning, we have the sphere, it's two-dimensional, but it is in 3 dimensions. And if I say that the position of, for example, if I say in this graph here that T1 and T2 are present, I know what they are, but I didn't observe T3. Well, I know that it must be along this line. So where it crosses the surface, I already know where T3 is going to be, and that's because there is this redundancy of the data. If I just give T1, then across this plane here, I will have a whole line where they could be line, and I don't have enough information at that point to get that. So I need an extra degree of redundancy. That degree of redundancy comes along this direction, and that is along the sequence. If the sequence is in time, like an utterance, it comes from the fact that the articulator positions at time t plus 1 are going to be very similar to those at time t because of the continuity. That means they cannot, if I reconstruct this value with an arbitrary value, then I have to make sure that it is not too far from this vector and from that one. That will help me to choose the right ones, if I have many to choose from. So I will assume that these observed vectors are actually samples of a continuous function of a variable set. This variable set would be the time for an utterance. I sample something in time, and I know that it depends continuously on that. It doesn't have to be just a one-dimensional variable. It could be two-dimensional, for example, something which is continuous on a surface rather than on time. And that would give me a different kind of continuity constraint, but it holds exactly the same. An example of that would be the wind field on the ocean. I can measure the wind. It varies continuously on the surface of the Earth, and I can use that continuity constraint to reconstruct it, given, for example, measurements of the backscatter with a satellite. Okay, so I will use several types of reconstruction here. The one that is normally used is pointwise reconstruction. It means at vector t of n in time, I select just one reconstruction for it. For example, I have the acoustics and I select one value for the articulatory variables, and I don't bother about what comes up before and afterwards in time. I select that one and I fix it. And that could be done with a neural network or any other mapping approximator. What I will do is use multiple pointwise reconstruction. That is, I know what the acoustics are. Somehow I'm going to produce all the appropriate articulatory configurations that map to those acoustics. And later I will choose from them. That is my multiple pointwise reconstruction. Once I have for every point in the sequence all my candidates to choose from, then I will just choose one. And that will give me a global reconstruction. And I will use the continuity constraint for that. So briefly, some of the related problems and related approaches for this type of problems. The one I mentioned is statistical mapping approximation. You have values for x and values for y. But first of all, I should mention that regression is a particular case of data reconstruction. In regression, always one type of variables are missing, and always the other type are present. For example, in the acoustic-to-articulatory mapping problem, it's a regression problem, regression of the acoustics to the articulators. Always it is the acoustics that are present and always the articulators that are missing. So that's a regression problem or a mapping approximation problem, which then is a particular case of this approach. So methods for that are well known. They are universal mapping approximators like MLPs, neural networks, or any other regression functions you want to find. And the problem they have is that they give you a single reconstruction, and they ignore multivalued functions. Imagine you have the function x squared, right? A parabol like this in the x and y axis. That works well when I map the function x squared. I give value of x and I get x squared, only one value. If I go from the y to the x's, then say I have the value 2, what is the square root of 2? I can have the positive one and the negative one. And a mapping approximator will not find that. It will find the line along 0, which is the middle line. It will give the square root 0 for any single value in that particular case. So that's why these methods are not suited for the problem when you have multi-valued mappings involved. In statistics, this problem has been recognized for a long time, and they use imputation modeling. What happens is that they don't approach the problem of reconstruction per se. They don't want to reconstruct the complete data as it was and minimizing some error measure. What they want is to fill in the holes with some values that are plausible, maybe not the right one, but they're reasonably plausible, and then use that for later inference. For example, to classify. You reconstruct your vector t, and then you classify it or do something else. So you don't care about exactly what the value of the vector t was. You just want to find something good enough that will allow you to do that inference. So those methods don't really apply here. But they are based on the conditional distribution of the missing variables given the present ones, which is what I used. And then there is vector quantization. It's a particular case of our method. And finally, sequential modeling with models like Kalman filters, HMMs, or any other trajectory model. These models model the variation in time, but I'm not really interested in that. I don't mind how the trajectory behaves in time. What I mind is that once I have that trajectory and it has holes, how can I fill in the hole? So it's not a reconstruction problem, the problem of HMM, for example. A summary of my approach then. What I do is, of my observed data that includes what variables are going to be missing and present, for example, acoustics and articulatory positions, I get a sample from that data and I train a joint probabilistic model of that. So a joint probabilistic model of acoustics and articulators. And I train that offline. So I need articulatory data for that bit. And then at the construction time, what I do is the following. How do I know what values can the articulatory variables take, given that the acoustic variables are these? What I do is I compute the conditional distribution of the missing variables, the articulatory variables, given the present ones, the acoustic variables. That conditional distribution is going to have several peaks, hopefully one peak at each articulatory position that is correct, that maps correctly to those acoustics. So how do I select them? Well, I take the modes of that distribution. I need a mode finding algorithm for that. Once I have done that for each point in my sequence, and I have all the candidates for that, then the reconstructed sequence is obtained by minimizing a global continuity constraint, as I mentioned. And that can be done conveniently with dynamic programming. So how do we estimate that model? In principle, you could use any method. You could use a mix of Gaussians or anything like that jointly for acoustics and articulatory vectors. What happens is that we know that those vectors have a low-dimensional representation. That's what we are going to use to reconstruct them. If they didn't, if they could be anywhere in the space, then there is no way I can reconstruct what is missing, because I just don't have any clue what it is going to be. Then this makes it, this suggests to use latent-variable models, precisely because they are well suited for that. But I have to say, they are not strictly necessary. You could use a mixture of Gaussians perfectly, because all I need is a joint density for the combined, for the observed variables, and I can use any model for that. I just want to know where in the space of the combined variables is it likely that I have data and where it isn't. So I will use then latent variable models, but they all tend to happen. They all tend to be in the end mixture of Gaussians. I just mentioned earlier that GTM, because of the discretization it had in the latent variable space, it tends being a mixture of Gaussians. Constraint to lie somewhere, but it's a mixture of Gaussians. Factor analysis is a mixture of Gaussians. It's just one Gaussian. So once I've said that, we cannot ignore it, and we can just assume that what I have is a mixture of Gaussian model on the whole space. And that's telling me where the data would fall. And from that, I compute conditional distributions. So I know what the present variables are at some point. I know what the acoustics are. What are the articulatory variables? I take the conditional distribution of the missing variables given the present ones. Assume, like here in this picture, that y is present. Y has some value. And I compute from my model, from my mixture of Gaussians, the probability distribution of x is present. And I compute the distribution of y given that value of x. Where is y going to fall? Well, looking at that distribution, the red one, here, clearly it would not fall here or on those sides. It's probably going to be in the modes or near the modes of that distribution. That's just because that's what the density model is telling me. It's telling me what areas of the space are likely to contain that value. So I could then, once computed the distribution, I could then say, given x, I say that y can be either that value here, or this one here, or this one here. It would be an error to take the mean of that distribution, because in this case the mean happens to fall there, in an area which is very unlikely to contain data at all. And that's what I was mentioning before, that universal approximators do. What they do, well, you can imagine that what the universal approximator does is converge to the conditional mean of the data. That's a theorem in pattern recognition. It means that given the value of x, and you have data everywhere there, it's going to find that conditional distribution, the mean of that. The mean is that one here. That means that using a univalued function, you find the best univalued function. You cannot do better than that. But that doesn't matter in this case because it's wrong anyway. You need a multivalued one. Sometimes it is going to be this value, sometimes that one, and a few times that one. But it's never going to be that one. So that's why you need to not to choose the mean, to choose something else. In this case, I propose the modes. Now, can you always do that? Imagine that this distribution, instead of being strongly peaked like this one, is relatively flat. Then I really don't know where the point should fall. It can be anywhere there. That is usually the result of a problem which is too under constraint. Like in the example here, if I say that T1 has a certain value, then I get T2 and T3 on a plane parallel to the screen, which gives me this intersection here. So I will get a probability distribution which is pretty flat along all that line. Any point in there could be likely. In a case like the one in that figure, I may have T1 and T2, and then T3 must be here. So I will get a conditional distribution that has a peak where it crosses the mapping. But if this manifold curves itself like this, then I might have a second peak up there. All that information is contained in the conditional distribution. So, in order to pick points from a distribution, that distribution should be peaked. And one way to measure that, which I call sparseness, how thin is the distribution around the peaks, you can use the entropy. But I haven't really cared about that. I have just always computed the modes of any conditional distribution and used that to reconstruct. And of course, for conditional distributions, like the ones that result from factor analysis, that are unimodal always, factor analysis is a single Gaussian, so anywhere you cut it to compute a conditional distribution, I get a single bump. So there I don't have any problem. I just have to pick the mean or the mode, which is always the same one. Those models are not good for this approach, and nothing of this would matter. So I developed an algorithm that, well, I assume that the audience is familiar with mixture of Gaussians. The properties they have that make them very attractive for this problem here is that, first of all, it is very easy to compute conditional distributions. In fact, if they are diagonal, all I have to do is to cross out rows and columns of the appropriate covariance matrices. So that's very fast. Second, they give me multimodal distributions, which I need. And third, they are universal density approximators. Just by using a lot of them, I can model very well my density. So I developed a method to find the modes of an arbitrary Gaussian mixture. So the picture shows a Gaussian mixture where the centers of each the components are all round, isotropic, and they are centered on the crosses. So there is one there, and so on. And the contour lines show how the whole combined density looks like. It has 3 modes in the the red triangles. Now, the method works as follows. Well, I have 3 methods actually. One is just gradient ascent. So you start somewhere, follow the gradient, and that will end up in a local minimum in one of the modes, in this case that one, for example. You can also use quadratic optimization. You need to compute the Hessian. That's easy with Gaussian mixtures. And then there is a third method, which is a fixed point iteration. That's also easy, thanks to the tractability of Gaussian mixtures. In any case, there is one further factor we need to take into account. I need to compute absolutely all the modes, because in my assumption, every mode is a likely value to correspond for the missing variables. So I need to do exhaustive mode finding. I have to find every single mode here. The way I devise for doing this is starting from every single centroid. And this lies on a conjecture that I have not been able to prove in the general case, which is that the number of centroids, the number of components I have in the Gaussian mixture is larger or equal than the number of modes. And also that those modes lie in the convex hull of the centroid. This is relatively intuitive if you think about it, but there is not a proof for that. Anyway, the algorithm does perform quite well in practice. And by starting here, I end up there, start here again, I end up there. From here, I guess I would end up here, and so on. So I do find all the modes. Okay, so, and I can also find confidence intervals for the value of that mode by locally approximating it using the Hessian.
When you're picking random seeds and just doing the gradient descent, how do you know that? How do you know that you hit all the modes?
I don't know. I don't know, but
this is an unsolved problem with modems.
That's right. It looks like a simple problem itself. Hasn't anyone thought about this earlier, finding all the maxima of a Gaussian mixture? Well, I don't know that anyone has tried that. And as I say, there isn't even a proof for this simple statement that if a Gaussian mixture has got m components, there are at most m modes. Imagine that if I have m components, I can have 2m modes. There is no way I can find them. But I hope that's not true. I hope I have less than m. And besides, I hope that this algorithm does find all of them. The reason for that is that the modes arise from coalescing components that are nearby, or just one component which is separate. So in both cases, the mode should be near one of the centroids. I don't know which one, but it should be near some of them, or halfway between them. So that if I start from one of those centroids, I hopefully should converge to that particular mode. And because there are fewer, in my assumption, modes and centroids, I should cover all them. It's a time-consuming process because I have to do that for every single component. But now, what happens is that if my model in joint space has, say, 1,000 Gaussians, a lot of them, well, that doesn't mean that the conditional distribution is going to have 1,000. Because when I cut somewhere, I say my x value is here, compute conditional distribution of y given x. A lot of those components are going to lie far away, and they have negligible probability, so I can discard them, and I reduce massively the number of components. Okay, so what this gives me, if I do this mode finding procedure at every point in the sequence, what this gives me is at point 1, I get, for example, 5 modes. And those are 5 possible values for reconstructing that particular vector. At point 2, I, in this case, would get 2. Sometimes I may be lucky enough to get 1, and then I know that definitely is that one. But in general, I can have several. And the problem is select at point 1 one of them, at point 2 another one, and so on. So I have to travel through that graph in an optimal way that I have to define myself. And so I need to minimize some constraint. That's the way I devised it. And that constraint would depend on the problem. If I don't have information about that problem, then I don't know what to do. But for the case, for example, of the articulatory parameters, I know that whichever vocal tract configuration I choose here and here, these two cannot differ too much. So I can define simply a continuity constraint there by summing all the distances between consecutive points once I reconstruct them with one of those points. So I choose this point here, and then in 2 I choose the second one. What is that particular distance? I add that. I add that distance. I go to the next one, I choose another one, and I add the distance. So altogether I have the length of the trajectory. I want the trajectory with the shortest length. And how can I do that? Well, this problem is a dynamic programming problem, and in a speech audience, I guess everyone is familiar with that algorithm. It's just what I need, and it's very efficient. So all I need to give is that graph, and it returns to me the shortest path. So that's what I do. And that's how I reconstruct the sequence. I will just illustrate it with a toy example. Imagine that my data now that I observe just have two variables, T1 and T2. But they are low dimensional, so they fall in this curve with some noise, but they fall around here. A sample of that data could be that thing for there. This is what I use to train my model. And when I train my model using some density model, I can get something like this. If I use factor analysis, well, I know that I'm going to get just a single Gaussian. It's going to be sitting on the mean of the data, and it's going to be oriented in a certain way that for this particular data set would look like this. If I use GTM, remember it's just a mixture of Gaussians, and they are round. So there is one Gaussian here, another one here, and so on. And GTM has modeled this particular red trajectory there. So the Gaussians must lie on it. Because I used a lot of them, I think I used 200 here, then you really don't see the difference. But there are many little blobs there. So that gives me a very good density model now of the data, of the joint data. Now if I take the conditional distribution like here, I say T1 is 0, for example, how about T2? Well, I will get a bump there for this one. If now I say, well, if T2 is 2/3 of pi, or somewhere here, for example, then this conditional distribution for T1 will give me one bump here, another one there, another one there. It is tracking the solutions of the inverse mapping, right? And that's just for one point. I don't know, for a trajectory like this, that could be sampled from there, and I have many missing variables there, I don't know which one to select. Well, I just repeat what I said earlier. I choose the closest one. So if at time n, I am here and my modes are there, I just keep these three modes in mind. The next instant, I don't know what T1 is, I know what T2 is. And I have these three modes, I keep them as well there. The following instant, I happen to know what T1 is, but I don't know T2. So I'm somewhere here, and I cross there, so I just get one particular point. Now I need to travel in that graph in the shortest path, which is this one, which would correspond to traveling like this. This would also be possible, but it has a longer length, and it's not going to be the trajectory given by the algorithm, and it's not the one we want, because it is jumping branches. And that jumping branch is what I want to avoid, because the mapping is continuous. That's the continuity constraint. So that demonstrates how the method works. It works fine for that toy model I mentioned. I tried all sorts of combinations, regression from T1 to T2, inverse mapping, which is multi-valued, or arbitrary holes in the sequence, and it reconstructs as well. I tried it also in this robot arm problem. So the robot arm is the one I mentioned before, and this is the x1 and x2 space, just like here. The robot arm is here. So imagine I give the task to the robot, follow this trajectory, perhaps because it has to pick objects along this trajectory. Well, I need to know then what the trajectory in joint space is. And because it is multi-valued, there is a problem. At that point there, I can have the elbow up and the elbow down configuration. But if I choose the elbow down configuration, I'm going to get into trouble as I as I move along, because it will have to change suddenly, and I cannot do that. I mean, if I play like a movie, you will see it very clearly. So the mapping from angles theta to position x is univalued and is known. The inverse happens to be known for this particular case. You can work it out analytically, but the idea is to use this when you don't know what the inverse mapping is, and you don't even need to know what the forward mapping is. All I need is a sample of data in joint and X space in this case. If you know the forward mapping, you can also use it to further constrain the data. It's obvious how to do that. You select a candidate reconstruction, and now you map it. And if it matches well with the data, then I can use that further to select. I could do that there, but I didn't do it. And the method reconstructs the trajectory well. So I'm going to conclude with the method and the presentation. The method was based on multiple point-wise, so for reconstruction of sequential data, on multiple point-wise reconstruction, using a joint density model of all the variables I observed, and using exhaustive mode finding in the conditional distributions at each point in the sequence. And I implemented it with Latent-Variable models or Gaussian mixtures, and the global reconstruction of the sequence was done by applying a continuity constraint implemented with dynamic programming. And I phrase this by saying that the most of the conditional distribution contain the potentially correct values, but the ones that are actual may be recovered using the continuity constraint. And some advantages of the method. It's applicable to varying patterns of missing data. Obviously, it is not of interest in practice, but if I have at some points the acoustic missing, at some other points the articulatory missing, the method still works, it's general for that. I don't know of any problem of use where you will have that. The closest two ones I know are in occluded speech, robust speech recognition. In the spectrum, you have some values that are gone because they have been occluded by the noise, and some are still valid. So that would be a problem where you can have from one frame to the next variables missing which are not the same. And the other one would be in facial and acoustics recognition of speech. Imagine a person is speaking, but sometimes there is noise and you don't hear what the person says, and sometimes there are objects or something that move in front of the person and you don't see parts of the face. That would be a problem of this type, but not very likely to. Other characteristic of the model or the method is that it is abstract. I don't need to know any forward mapping or any knowledge of the physics or the articulators or anything like that. I just need a sample of that data, and the probability density is going to capture all that for me, hopefully. Then it is insensitive to time warping because it depends only on the arc length of the trajectory. That's what I am minimizing. I don't mind how fast you are traveling through that arc length. That means, for example, I don't mind how fast you say the utterance, because it is going to go through the same places in principle. It just is going to travel through them faster. The method uses only the trace of that mapping, the arc length, and therefore doesn't vary. It can give confidence regions also for everything you reconstruct, and it doesn't suffer from numerical instability or out-of-domain patterns problems. Imagine that at some point, say, the acoustics take a value, a negative value, or something that cannot happen. For example, for the pitch, imagine the pitch becomes negative. Well, the model would not care about that. It can still compute conditional distributions. Why would a pitch become negative? Well, it may become near zero, and because of noise and things, move to the negative region. In some methods, that would be a problem. But with probability models, that's an advantage. And the disadvantages are something I have not talked about here, but it is that if the model is not smooth enough, instead of having one mode for each appropriate solution, you may have ripple around. And that can happen particularly with Gaussian mixtures, because if the Gaussian components are separate, are not very strongly overlapping, then you get that kind of ripple. And each of those points is a mode. So I get a lot of candidate reconstructions, more than necessary. And that can sometimes lead to a wrong global reconstruction. Then, when there are many missing variables, the mode finding step is computationally costly. And a problem which is general for density estimation is the curse of the dimensionality. It's very difficult to estimate good models in high dimensions. And finally, some extensions of the method. I have talked about continuity constraints, which are first, is a discretized version of the gradient of a derivative, but depending on the problem, you may be more interested in the smoothness, which is a second order differential operator, as a constraint, or quadratic. The quadratic constraint has been used in other methods for the articulatory mapping, where you can assume that a potential energy of a hook spring is quadratic. It has an equilibrium position, and the farther you go from it, the higher that energy is. So you want to minimize the energy. That means that the articulators are going to use minimum energy, so minimum effort for linear forces, and then you can use that as well. I have talked of reconstructing sequences, but you could also reconstruct fields as long as continuity holds. You would just need to use two-dimensional constraints there. And then there's a problem which is called in dynamic programming unbounded horizon. If your sequence is infinite, like a person speaking endlessly, then where do you stop to reconstruct? You can stop at the point where you have only one candidate, but that may not happen. Efficient estimation of smooth density models, as I mentioned. And then this is, for me, perhaps the most interesting approach. Instead of looking for the modes, which sometimes can be misleading if you have ripple, like this, what you really want to look is at the whole bump. But identifying the bump is not even well defined. A mode is very well defined. You have zero gradient there. But a bump is more difficult to define, but it probably would be more useful. And this ends then the method, so I will just recapitulate what these models do. I have presented the general class of continuous latent variable models, which aim at representing high-dimensional observed data, which have intrinsically a low-dimensional representation. And then I have shown how you can use these probabilistic models to construct conditional distributions that can be used for dimensionality reduction and then for general sequential data reconstruction. Thanks, and any questions?
You said that the problem of finding the bumps is not well defined. It seems to me like it's very similar to clustering.
It is clustering.
Modes together.
It is clustering. But how big is the cluster?
Depends how you define the distance between the modes.
Well, I can give you many examples where a human would say, yes, there is one single bump there. So imagine you have one bump here and then just a little bit there. Is that one or two clusters? You can get, it's not well defined, I think.
But you can.
You don't know whether one point is in the cluster or not.
You can still do the clustering with respect to your results.
Yeah, I mean, I don't say that you should not do it.
That.
I personally think it would be a better approach than the modes, and it would be even faster. I just don't know exactly how well it's going to perform, how you define, as you say, distance and things, and how you cluster. For example, take k-means. In the k-means algorithm for clustering, you need to know what the k is. And there are tomes of literature on how to find the appropriate number of clusters. And just because we don't know exactly, it's a big problem because it's not properly defined what bump means. But nonetheless, it does have, I think, a use here, a significance. And I said that it would be faster because in this case, you're clustering your Gaussian components. I think that would probably lead to a faster algorithm than just searching this high-dimensional space for modes.
Have you considered the problem where it's not clear whether when the data is missing versus when it's not?
Right. Mm-hmm. I have not. But it is a very interesting problem and difficult. In the case of occluded speech recognition, which has been analyzed in my previous university in Sheffield, that's one of the efforts that they have done. They use spectral subtraction methods typically, and there are other methods. What you do is basically compare how strong the signal is compared to how strong the noise is at a particular time and band of energy. And if one of them is bigger, then you assume it's present or it's missing. But it's not a foolproof method. For other problems, I really don't know. The method assumes you know what is present and what is missing.